Okay, right. First of all, thanks for introducing me and for having me, Tuan. First questions, can you see the slides?
Yes, we see it.
Awesome.
Yeah.
Okay. So as Tuan said, I'm Alexander Nenninger. I'm from NTT Data. I work for NTT Data still. And we are currently in the process of building up the quantum team. And today I kind of wanted to give maybe a brief introduction into the basics of quantum computing, because I noticed that there's a lot of misconceptions, a lot of like maybe high-level understanding about quantum computing, but there's still very little understanding among many people how the actual computation happens inside a quantum computer, how we can imagine that. And that's what I wanted to talk about today. You're not really expected to like understand all the formulas that I'm presenting here immediately, although please interrupt me if you have like zero imagination on how things might be happening. Then we can just take a break and I can maybe work with some more visuals. But overall, it will be quite technical, and I hope you can excuse that. Yeah, so let me start with an introduction. I mean, the first question with a new technology always is like, what is quantum computing even? Why should I care? And basically, what it boils down to in quantum computing is the physical limits of computation and computational hardware. So we started in the 1900s with a vacuum tube. I mean, there weren't really any computers yet, but we at least could switch electricity with other electricity, which is nice. Then the transistor was invented in the late 1940s. Then also in the 1940s, the first computers emerged. In the 1960s and 70s, the first really integrated circuits were built, and like circuit size and feature size just shrank and shrank and shrank. I mean, you all know Moore's law. Basically, every couple of months, every year or so, the feature size halves, which means we have an exponential speed up in computation power. But unfortunately, there's limits to that. I mean, we are currently at somehow like 3 to 7 nanometers per feature. We are getting at the size of single atoms, and you can't like half single atoms. You can't make smaller resistors currently than single atoms. And it also the cost of producing new architectures scales exponentially now. I mean, there's just like about 3 companies that can do that, and it's just not sustainable. So we need to find like new ways we can do computation to keep scaling, to keep growing this field. And basically, that's where the idea of quantum computers comes in. A quantum computer is basically a machine that performs calculations based on the laws of quantum mechanics, which govern the behavior of the nature in which describe the behavior of nature on very small scales, so subatomic level electrons. That's it. So basically, a quantum computer does an experiment, and you measure the experiment, and then you infer some information about. You let this experiment do some computation for you, depending how you set it up. Where does the idea even come from? So, I mean, Richard Feynman it's much cited. He's not the only one. I mean, this like idea developed over decades. But in 1982, Richard Feynman proposed that, a famous physicist proposed that the idea, basically computing quantum properties of materials is very difficult on classical computers. But maybe you can use quantum computers to compute quantum physics. Well, that was the base idea. In 1985 already, David Deutsch developed a quantum Turing machine. Basically, it shows that you can do any computation that you can do on a classical computer. In theory, you can do on a quantum computer, which is nice. Then 1994 was a very much of a breakthrough. Peter Shor discovered a quantum algorithm that can factor very large numbers in polynomial time. This is very rare, very significant, because factoring large numbers is thought of as people believe that factoring very hard numbers on a classical computer cannot be done in polynomial time. You need at least exponential time. It hasn't been shown yet, but nobody has ever found a counterexample. So and people have been working really hard on it. So people are very sure that this is a very hard problem, factoring very large numbers on a classical computer, but it's a way easier problem on quantum computers. And then finally, in 1997, that's the other big quantum idea, or quantum, is that Love-Grover develops a linear search algorithm, which actually doesn't need to look at all the elements in the search space. So given us a list, and usually on a computer, I mean, to find an element in a list, you just check every element, or at least you have to check it. And I mean, you expect to check at least half of the elements. So you've got a complexity classically of O of n. But on a quantum computer, you can actually, if you have a function that queries that list, you can actually find the element in O of square root of n, which is, it's a neat trick. And that's basically where people hope to get a quantum advantage in optimization problems, for example. Turing salesman is one classic there. Before we get into the nits and weeds there, I wanted to put up a bit of a disclaimer. There are multiple formulations of quantum mechanics and generalizations of the mathematics we discuss here. I tried to make a very basic version, basically I tried to boil it down to everything that needs to be there for quantum computing. Quantum mechanics is a way more diverse field. There's way more to discover, basically like in any science. Also, there's competing formulations, but that are equivalent, but maybe are a bit of a different represent a bit of a different viewpoint on the subject. Yeah, and here on the right, you can see I made a quick graphic. So you're trying to find a certain bit string among all possible bit strings of length n, and typically you'd have to try 2 to the n bit strings to find the right solution. So that's a scaling of exponential scaling in this length of the input. But on a quantum computer, I mean, even though you still have exponential scaling with a quantum computer, exponential scaling of root of n is way better than exponential scaling of n. So if you can achieve that, that's amazing. Let's get into the bit into the weeds. How do you compute on a quantum computer? It's not like you have bits. You don't have ones and zeros on a quantum computer. You kind of have, but they're a bit more complicated. And for now, I just want you to forget your intuitions about computers. Just think about maybe the geometry that I'm going to present. So the first primary basic that we need is, I mean, you might remember that from uni or from school. So some Leistungskurse, I don't know how that's said in English, introduce complex numbers. But basically what you do is you add a second direction to the real line. So you take the real line here on the right and you add a perpendicular direction to that and call that the other direction I. You can then write every complex number as some real component in this direction and some complex component up there. It's just a point in the plane. And the nice thing about this is you can define I to be I such that I squared equals -1, which in the real line, I mean, you can't get negative numbers. You can square any numbers and get a negative result, but there it is. And what this means, actually, what this forces is that multiplication by I results in a counterclockwise rotation of a point. So basically, if you've got a point there, you multiply by I, get IC, and it's just a 90-degree counterclockwise rotation. There's not, complex numbers have a bit nicer algebraic properties. So any polynomial, I mean, if you're into polynomials, that's fine, but it's kind of necessary for quantum computing to have like an easy to use basis. And then basically, one tip for the programmers among us: if you have anything that's rotation or translation or anything that requires manipulation in two coordinates, just use complex numbers. It's so easy. They just they feel like real numbers, but with some extra functionality. And one quick definition is that we might need to remember for the next slide. The complex conjugate. What you do is basically you take your point C, and you reflect it across the real line. So basically C is A to the A plus IB. Then C bar is A minus IB. It's just a definition. I mean, there's not much to it. Yeah, so please interrupt me if you have any visual, in your head, the move in your head stops. Next thing that we kind of need, but this is a somewhat similar idea. I mean, you also have points in these spaces, vector spaces. Oops, sorry. Well, vector space is a very simple object. Basically, a vector is just you put a couple of numbers in a list, in a fixed length list, and then that's called a vector. You can take elements of C for example. You can take elements of R, but we are going to use C for that. We define two operations on vectors. Basically, we can still add vectors, so that happens component-wise. So you take if you want to add vectors V and W, you just take the first component, add it to the second one, take the second component of V, add it to the second component of W, and so on. That's addition. And you can the second thing that you can do is you can multiply by elements of C, for example, and that's just stretching the vector out. I mean, I've drawn this here. So basically, if you have a vector V, it consists of two components. I mean, if you multiply it by 2, then you just stretch it out to make it double the length. And if you add two vectors, then if V and W, basically you just where's my mouse? Basically, you just take add the two directions together. So basically, if you add V and W, you walk V, walk in the direction of V, then you're there. Then you walk in the direction of W, and whoops, and suddenly you're on a certain point. If you hear of a vector space, then that's basically just all the possible directions you can have with with all the possible vectors you can have. I mean, there's not much complication to that. And finally enough, quantum physics uses kind of funny notation. So I mean, we typically can donate vectors with just a letter. Quantum physics uses these kind of parentheses. So if you see the vertical line to the left and an angle bracket, whoops, to the right, and that's a cat. And basically, if you flip a vector to its side, you transpose it, and apply the complex conjugate, you get a bra. So basically, that's just a kind of a punny thing. So a bra and a cat together is a bracket. And they fit nicely together. So basically, you can glue bras and cats on the vertical line. What's a Hilbert space? Hilbert space. It's got already spaces that already have the name of a person. Maybe it's complicated. it's actually not too complicated. So again, every Hilbert space is a vector space again. So basically just a bunch of directions. And well, we again define V and W as vectors. And Hilbert spaces have some extra operations. So basically in a Hilbert space, you can always take the conjugate transpose. Basically you conjugate each component of the vector and then flip it on its side. What this nicely allows you to do is define something called an inner product. Inner product is somehow related to the angle or the length, the angle between vectors. So if two vectors are orthogonal, then the inner product will be 0. If two vectors are perfectly aligned, then the inner product will be just the length of the it's harder to describe, but the inner product will be maximized. I think it's the mean of both vectors, of the length of both vectors. But basically the inner product is what you do is you squish together a bra and a cat. And what do you think about it? And and that's an element then of the like underlying field, in this case C. And what you do is basically you take the first component, basically you just multiply each component, each corresponding components and sum them up. Well, if there's inner product, then who would have guessed there's an outer product too. And that's just some kind of weird operations that one has to get used to. Basically, if an inner product combines two vectors for each component, outer product generates all the possible combinations of vector elements in a matrix. So you multiply a cat and a bra, and then you get some very big matrix there that's decided that's as low, and then the first first entry you take the first component of the first vector of V and the first component of W, and you go, sorry, there's a mistake there. This should be actually, and then here you take the first component of V and the nth component of W. Sorry, there's a bit of a typo in there. And here you take the nth component of V and the nth component of W. Just all the possible combinations of V and W. The final thing is, if you have got a direction, you kind of also have a length, or how far away from 0 you are. And we write this as a norm. So basically just the length of any vector. It's called the norm. And I also can calculate it actually from the inner product of the vector with itself. That's a bit of Euclid there. Interrupt me if like you have zero imagination again, but otherwise I'll continue. I can't see you, unfortunately. So what even is a qubit now? I mean, we've got all these like abstract ideas, but what is a qubit? Basically, a qubit is an element of like C2. So if I take a vector with two directions here, or two components, that's a qubit. I mean, you also have to assume that the length is 1 of this vector, but that's not super important. The important thing is that you can basically have a direction in space, and that's a qubit. So, and the second thing is, how do we, like, that a very neat trick about qubit is not how they combine. So basically, if you for example combine two normal bits, then you would just concatenate them together. You would, like, some normal data, some classical data, you just concatenate the data. With qubits, it's a bit more involved. The thing how two qubits combine, basically two qubits combine by the outer product. So suppose we have a qubit V and a qubit W. Then it's just you combine the first component, multiply the first component of V with the first component of W, first component of V with the second component of W, second component of V with the first component of W, second component of V with the second component of W. So kind of mix all the possible combinations of qubit states together. That's like really the core trick to quantum computing, that you can operate on, you get an immense amount of memory for very few qubits. I didn't talk about it, but basically any vector that you can have in 2D, you can decompose that into maybe if you go back. So if you have any vector in 2D, like here V, you can decompose that into two perpendicular directions. So suppose we choose any two perpendicular directions, we can just project the vector V onto the first basis vector, what we call them E1 here. We project it on the second basis vector E2, and then so we can decompose it, and if we sum E1 and E2 with some prefactors, then we can get V back. That's very nice because we can actually have coordinates this way. And we can like have some sort of notion of bits in qubits, because like that direction doesn't really know what bits are, but if you choose a basis, then two basis vectors, then we actually get some sort of bits. And what we do is like we just choose the vertical direction, we call it 0, and the horizontal directions we call it 1. And any qubit really is a combination, or is a sum of some prefactor alpha times 0 plus some other prefactor beta times 1. And due to because we want to work with probabilities later, we also want that our alpha squared plus beta squared equals 1. Simply means that each qubit actually, or each vector, has length 1 in the end. Yeah, so multiple qubits combined by the tensor product. And the combined space, then of course, like what are all the possible qubits or possible states in a 2-qubit system that we could have. Described it with like the outer product on vector spaces. So basically this notation just means take any vector in C2 and take any other vector in C2, apply the outer product, and then that's all the possible like states that you can have in a 2-qubit system. And we kind of, yeah, here's a little bit of a graphic. So we kind of have like one direction, one qubit there, and then that can be decomposed in like a vertical and there's a bit of a weird trick, but in another direction, in a 0 and in a 1. Okay. What does this mean actually? Like, what's the trick with qubits there? Why is this useful? So let's say we have a finite number of qubits or bits, maybe a classical register, a classical piece of data can have 2 to the n different states. That's also already a very large number. It grows exponentially, which is nice because we don't need very large computers. Thank God. Thank God your laptops can be small like that and hold on a massive amount of data. But we can have 2 to the n different states. Like for every possible bit, you can choose whether it's 1 or 0. And then you just multiply each of the possible number of choices, and that's like 2 to the n. But the crazy thing about qubits is that a quantum register can actually have 2 to the n different states. So for one state, that doesn't matter because you have 2 to the 1, which is 2 to the 2, which is 2 to the 1, so you have 2 to the n minus 1, sorry, again a typo. Maybe I should correct that, but basically the qubits, the number of possible, like the size, the information content of qubits is way higher than that of classical systems or classical bits. It's also nice because this outer product structure basically means that you can have some sort of interaction between any possible subsets or subset of your states, of your qubits. So for example, if you have 3 qubits, then you can have an interaction or have some sort of operation on only just 1 qubit, or you can have an operation of either the first one and the second one, or the second one and the third one, or you can have an operation on all 3 combined. This means that you can have basically you can have perfect data parallelism. Yeah, a qubit you can act on all the qubits at the same time with one action or one operation. That's what's exploited in Shor's algorithm. The problem with this is, of course, then how do we define these operations? You know, if you have like so many possible operations, it's very hard. Like storing each operations by itself is very difficult. And also there's like no real way currently of storing qubits long term. They're all just disintegrating or decohering what we say in a couple of milliseconds. And what we really need for industrialized applications is when you read, people have invented QRAM, so random access memory for quantum computers, and there's currently no good concepts for that. Here on the right-hand side, I've plotted again like how the memory grows. So for 1 qubit, it's the same. 1 bit or 1 qubit, the memory capacity is the same. You can see that quantum memory just goes through the roof much quicker. So next question then, of course, is how do we actually perform computation on qubits? I left out the details. I have a slide that goes very much into detail later, and we can discuss that. But for right now, basically a qubit, or like a qubit computation, a quantum program, or quantum circuit, how it's often called, basically consists of 2 steps or 3 steps. First is you prepare some initial quantum state that's basically just some rotation in very high dimensional space, some direction, very high dimensional space. And that's your starting point. That's maybe your input data. The next step is then to apply a quantum algorithm. A quantum algorithm can consist of rotation or reflection in that space. So you can think of directions, you can rotate them around the center, around the origin, or you can reflect them in the other direction, or you can reflect them around some other quantum state. That's all you can do. So that's very, for example, very natural in machine learning, where also you usually have a lot of linear algebra, and you can think of maybe doing linear algebra directly on like physical systems, and you don't need like simulate it on a computer. Then you get some sort of computed state, phi1. And this computed state lives in your quantum register. And the next thing is, this kind of a trick with quantum computers is you have to measure. Like you can't look at quantum state and see, oh, that's the quantum state. No, you can't do that. What you can do is measure. Basically, if you have any quantums, let's say you have a qubit that's 45 degrees in like a diagonal direction. You measure, and then you either get 1 and you project it down onto the 0, or you get a 0. You get a 0, sorry, you get a 0 and you project it down flat, or you get a 1 and then you call it 1. The result of your computation, you call it 1. If it gets projected onto the vertical direction. And basically what this process is inherently random, so you can choose which one is going to happen. You just have to repeat this a couple of times. And once you repeat it enough, you can estimate the state of your qubit before you measured. And so this is quite a bottleneck. Like this is like the way how you get data out of a quantum compute, and that's quite a bottleneck at the moment. So you measurement is an inefficient process. It scales only with the accuracy only scales with O of square root of n. The number of measurements you do. And for very large circuit, you need to measure even more. For very large states, you need to measure even more. It's kind of currently a very hot topic in research. And in the end, if you don't measure like all of your complete quantum state, you get the rest of your quantum state. Basically, let's call it rest. I don't want to go into detail. You can retain it in your quantum computer and do further calculation. But the thing is, like your computed state is, by measuring your computed state, is destroyed. So you'd usually start from the beginning. And basically, I just wanted to make some sort of visualization, like how a qubit moves, or how our quantum computation actually like affects one qubit. And what you can see is basically I've animated one qubit, and you can, for example, also only apply a little bit of a quantum computation. And basically in each time step, I apply a little bit, and after a certain time step, it stops, and then that's the quantum computation. And you can see you can have some sort of rotation in a qubit, and you can have reflection, and that's it. What's the time? 34 minus 10. Okay. Maybe some quick words about current quantum computing approaches. There's currently two main branches of quantum computing. There's gate-based quantum computing, which is like a general approach that I just presented. And you've got superconducting hardware, you got ion traps, you got photonics. I've put some logos there. IBM and Google are superconducting. They're currently the fastest quantum computers, but they're kind of hard to manage. Ion traps use physical ions on a grid in a magnetic field and manipulate it with lasers. Kind of slow, and photonics can't be reprogrammed, but are very stable and are very fast. The other thing is adiabatic quantum computing, which is a subset of gate-based quantum computing, but it's easier to implement in hardware. And NTT, for example, has the coherent Ising machine, which there's also some digital stuff where you simulate quantum computing. I don't see very much future in that, to be honest. And there's quantum annealing with D-Wave. And yeah, this is just a quick overview over different hardware types. The most important one is probably trapped ions with, you have them in a magnetic field and you manipulate them with lasers. And the other one is like superconducting loops. Basically, you've got a resonating circuit, and that's like not a physical quantum computer, but it's like a quantum system. So thanks for your time. I can answer questions now or later. Yeah. Hope it was at least somewhat helpful.
Alex, thanks a lot. Thanks a lot for your presentation. So guys, now is the time for question. And since we are big group, since we are a small group now, so feel free to ask any questions, and feel free to open your camera as well. So yeah, any questions for now? Yep. So I have a question, Alex.
Yeah.
What do you think would be the? So what do you think is the challenge for mass scaling of quantum computing?
Hardware. Hardware is difficult. Only a few companies are doing it. It's super fuzzy. So basically, if you have, for example, with superconducting loops, they have to be cooled to very low temperatures. And if the temperature is just a little bit too high, you get interaction with the outside world, and the outside world will destroy your quantum state. And you already make errors. And so basically every quantum computation currently in the NISQ era, we call it NISQ, like near term intermediate scale quantum computers. Every like quantum computation, bit of quantum computation makes error in the rotation, like you rotate a little bit wrong, you need to correct that. And that's also very inefficient at the moment. There's very much going a lot of research into that.
Okay, so it's very hard to produce the hardware. That's what you say.
So
and
you don't.
That's why it's expensive. Huh?
Yeah. So you don't need very many qubits to do something useful, but you need very high quality qubits. And the term to look out for is when somebody publishes anything about logical qubits. Logical qubits always mean perfect qubits. That's what you count on. Like just qubits on itself, like physical qubits, are not very great if they're not high quality.
Can you hear me now?
Yeah, we can hear you.
Okay, sorry. New setup. You say you don't need many things. I mean, I was listening to your talk, and I was wondering. You said that to measure this quantum state, I assume you need to measure effectively a number of say items, of atoms, of ions, whatever, to be able to get out the state, including the phase. I mean, what kind of a volume of carriers are talking about? I was talking about 1,000 ions that need to be measured here, or are we talking about you know, a number of frequencies in some solid state? You very briefly showed something about the hardware and then the carriers of the quantum state, if I may call it that. We have a number of things here, but I suppose you do need a certain number of carriers, right, of these qubits. Yeah, so the number of carriers basically determines how much memory you have available. And I mean the memory grows very quickly, but error correction can reduce the amount of available memory by a factor of 1,000 at the moment. So this is if you have 1,000 qubits, then you can have maybe five logical qubits. So this is quite an issue. I would imagine that the number of measurements is not a problem, because you can just restart this process again. Like you can make this in a classical loop. You prepare your initial state, you apply your quantum algorithm, you measure, and then you get a different result. But you can estimate the quantum state that you have here this way. But I do think that we're still quite far away from practical applications here, right? Because I mean, the technical intelligence still seem to be quite substantial to build larger systems. I mean, anything approaching a present-day PC, I would imagine, with its vast amount of memory or states that we have in there. These are still pretty much theoretical systems, aren't they? Yeah, so you will never replace classical PCs. I mean, that's so you will see quantum computation as some sort of accelerator, I think, in very specific tasks where they're needed, but we'll stick with classical PCs for a very long time. Okay, thank you. They're just better at basically all the useful tasks, like running Grafana or whatever, or running CI pipelines. Just use a Linux server, you know, just does it. Thank you. Also, maybe one quick comment. So adiabatic quantum computers is kind of closer. So DWIF has a production system. Their performance is in some cases competitive with classical optimization solvers. In other cases, classical optimization solvers just wreck D-Wave. Same thing for our NTT Coherent Ising machine. I mean, it's not still in research, but still in research lab, but we can solve large problems on it. In some cases, it works well. In other cases, like just use Gurobi.
Okay, so one last question to Alex. Anyone? Then I have one last question, Alex. So what currently, what is application for quantum computing? What is a real life application for quantum computing?
So maybe let's go back to the gate, to the different approaches. So for gate-based models, there's currently there's no competitive real-life applications. Just I wanted to be clear, but there's things people are looking into and so in terms of computing, you have, for example, actually calculating quantum mechanics. That's like quantum chemistry is the buzzword there. That's kind of hard to do. Then you have some machine learning applications. So if you go back to the quantum computing model, you can maybe think of your quantum algorithm as some sort of parametric function that gets applied to initial state and spits on our state. Looks kind of close to a neural network where you have some sort of parameters and you have some sort of function, and that function that depends on the parameters, and you can have some sort of input and have some sort of output. And that's currently what's called variational quantum circuits. It's not for practical tasks, just use classical machine, use decision tree or XGBoost. But it's interesting. So that's one application. What I feel like is more competitive, at least what you've seen on specific optimization problems, is an discrete optimization problem is a problem where you have many tiny decisions that somehow depend on each other, and you want to maximize some sort of function that depends on all of your tiny decisions, and you have some sort of rules about what's compatible and what's not. And our current Ising machines in some cases shows very much a lot of promise, and it's also very large already. Also D-Wave has some sort of mixed hybrid solvers there that mix classical computation, quantum computation is also kind of interesting already.
All right, Alex, thanks a lot for the talk.
Yeah, hope you had fun, some fun at least.
Yeah. So at the end of the sessions, we still have a short socializing session. So there's still a chance to ask Alex more questions.
Yeah.
And now we move to Wolfgang. Are you ready, Wolfgang?
Hi, yes. Let me see if I can already share my screen.
Yeah, the stage is yours.
Let me know once you can see it.
We can see it now.
Okay, fine.
Okay.
So I'm going to talk today a little bit about the CDK to create resources in AWS, how to do so, how to also use AWS code pipeline to deploy it in a way it can serve in professional environments. Before this, maybe let's have a short overview on the alternatives on infrastructure as code, and why I picked here CDK as a topic and not the other two alternatives. Before I show some slides, I have quite less than Alexander. There's a little bit more hands-on stuff after the slides. Here some resources where if you're interested in this topic and you maybe want to read again something about it, you can find here in my blog. This is the introduction, the infrastructure as code comparison, and after this, it's the topic is as mentioned CDK. So here you find some blogs about CDK. Here's also one about one of the topics we're gonna look in detail, the how to deploy the CDK resources with the code pipeline. And here is my GitHub. So just look for GitHub Wolfgang Unger, and here I have multiple repos there. But for example, this is the example I'm going to show the CDK code pipeline. You can just check this out, clone and deploy in your account. You have to adopt some small parameters there in the CDK JSON, but then it should be run in general. Okay. So let's start with a short overview on the on the options which we have to create infrastructure as code on AWS. So it's basically CloudFormation, Terraform, and CDK. And what are kind of the strengths, or what are the advantages or disadvantages of these, or what are the attributes of features of kind of these tools? CloudFormation is AWS native. It's based on text files, either JSON or YAML. It works on AWS only, so it's not cloud agnostic like Terraform. So you really stick to AWS in this case. So you create a CloudFormation template, a CloudFormation stack, and you can code your resources there, a group. And one of the big advantages comparing to Terraform, for my opinion, is it's a zero client approach. So you have nothing to install on your computer. You just have these YAML or JSON files, and so that's a stateless approach. Features on the language is you have the syntax of CloudFormation. So you have limited features there comparing to CDK or also sometimes to Terraform, but you have some conditions and stuff. So you have maps and these kind of features CloudFormation offers. Then also you group your stacks either in nested stacks or in stack sets. You can use also these two kind of features to avoid code duplication, but it's not the natural kind of use case for actual nested stacks and stack sets. In general, it's a text-based tool, as mentioned, and sometimes you will run into code duplications. Terraform is from HashiCorp. You can not only use it for AWS, but also for other cloud providers, for Azure, for Google. The language is HCL format. It's kind of a JSON indeed. So if you use the JSON, you will get along with this. One of the big advantages, at least in theory, is the cloud agnostic approach from Terraform. I would say one more thing on this. I have never seen actually a company who really migrated a big environment from AWS to Azure or vice versa. So it's, for me, it's kind of a theoretical point, this cloud agnostic feature, but let's call it an advantage. So you group like Terraform your files in your resources in files. You have modules also there. One of, for me, the points which is a disadvantage, you have a local installation. So also you keep a state, which can sometimes cause problems if you work in bigger teams, and also if you work in bigger teams because of these local installations. Terraform releases quite often new versions, so each team member get ready to be updated to the same Terraform version. If they differ, you might run into problems when the people deploy from different versions. You have a couple of advanced options. You have modules, you have for each, you have loops, and quite some features, but still it is text-based. And there's also a CDK for Terraform, which offers quite more features as the CDK, which we're gonna look next. But using Terraform in the classical way is like CloudFormation, basically text-based. So the CDK is, of course, it's depending on the client, but if I have a free choice, I would always select CDK. It's again a AWS native tool, and you have a programmatic approach, so you can really code in. It's supporting 5 languages: Python, Java, Go, TypeScript, or .NET. And so you can pick up your favorite language. I have a strong Java background, but concerning to CDK, I prefer coding in Python because it's more lightweight than Java, and it works perfect for me for CDK. And the big advantage is here, you can really use all feature languages of an object-oriented language like Java or Python. So you can create classes, subclasses, you can use inheritance, you can use polymorphism, and all of these features which you don't have in Terraform or in CloudFormation, because they're like Terraform introduced for each loops, right, as a kind of a language feature in there, but it cannot compare with features you get supported by Python or a language like Java, right? So we're gonna see this also in the project, and this is very useful, for example, to avoid paste in copy code. So if you want to create like maybe 40 EC2 instances, you think you have 20 is this kind, 15 of this kind, and the last 5 are different. You could create a superclass with the common attributes, and then you would group the 15 in one subclass and the other in these, and get can really use this kind of features which you already know from software development. Okay, so what do we have here on the CDK side? We have constructs, which represents the resources you create on AWS. There are different kind of constructs. They're like named L1 or level 2 or level 3. So based on the abstraction level kind of. So the L1, for example, they have a prefix CFN, for example, CFN load balancer or something, CFN lambda. And they're straight kind of close still to the CloudFormation file, which is going to be the output, which is going to be generated by your CDK. So these are the less abstract classes and need the most kind of coding, because kind of include all the parameters you would also code on CloudFormation side. Then the level 2 have a little bit more abstract level, more functional API. So you can use these normally use level 2 classes a lot when you write CDK code, and level 3 are kind of compositions. Like for example, you can create create a ECS service with some level 3 classes, which already contains a load balancing and auto scaling and kind of full package of related classes and resources you need to kind of run a service. You can also, of course, create your own constructs. And as mentioned, you can use your language features of Python or Java or whatever, and create kind of superclasses for your common needs and subclass for your project, for your branches, for your special cases. And then on the higher level, you have the kind of the stacks, which represent in CloudFormation a template or a stack where you include your resources. So these stacks really are going to be generated with the synthesize command and then deployed on AWS. How would you deploy CDK? So if you get started and you set up a CDK on your machine, you will run your commands like CDK synth, CDK apply, and so on, deploy. That's one way to get started. Of course, this doesn't work for a sophisticated project with a development team. It's not a good approach. And therefore, you need some kind of CI/CD. So one approach for this could be the code pipeline, which I'm going to show here on a kind of deployed example. This is also the example code from the GitHub, which you can clone if you're interested in how to create a CDK code pipeline with on your own account. So for this, for the CDK pipeline, you need basically 2 classes from the CDK. It's a code pipeline, which creates a pipeline, and doing a little bit more stuff, of course, but that's the main resource. And you add to your pipeline actions, approvals and stuff, and the main issue is to add a stage, which represents one stage in your setup of AWS stages or accounts. So for example, if you have 3 accounts like a dev, a QA and a prod, each of these is going to deploy it from a stage. Okay, that's so far from this slide. Now maybe let's have a look here how this looks like. I'm gonna open this project I have shown in the GitHub. And as we can see, if you're a little bit familiar with CDK, first one of these, this
Sorry,
file is,
could you
yes.
zoom in a little bit?
Oh,
Just
yes, sorry.
small screens.
Let me see. Yeah. Can you see better?
Wonderful, thanks. Need new glasses.
Okay. This CDK JSON file is the first thing you have to adapt if you check out this project, and you have to change here the accounts, which are now pointing to my account. Right now I have real numbers in there. After this meetup, I'm gonna put in there some X's again to check in my GitHub. But if you run it really on your account, before you start deploying and run the pipeline, of course, then you must also check in here this file with real account numbers and with a real code star connection. Otherwise, it wouldn't work because, of course, the code pipeline reads from the Git, right? So if you have still here dummy numbers, it cannot work. So, but the main thing, as in any CDK project, you have an app Python. This is a Python example where you kind of create the main files, for example, which normally would point to a stack file. In this our example, the important thing is not we add here a lot of stacks. No, we are adding here really the pipeline stack, which then creates the pipeline, and the stacks and resources we want to deploy in our project making part of the structure here are getting deployed from the pipeline. So if you look at the project, let me see here. For example, if we do a CDK list, this will list all these files we got here in the project. And there's one important issue. Our pipeline is gonna deploy the resources we are coding here in our project as we do this in a CDK project. But the pipeline itself is the only class the pipeline cannot deploy, right? It has to be deployed first time really with the CDK deploy command. So as we can see here, these are my two pipelines I have here in the app file, and these are all these files which are going to be deployed by the pipeline then later on. I have also some bootstrap roles. So you would need, if you set up multiple accounts, for example, you would have the pipeline defined in a toolchain account, right? So actually, you can see this also here in these CDK JSON. You have 4 accounts here defined. So you would need a tooling or a toolchain account for the pipeline itself, for the CI/CD DevOps stuff. Then you have your account, if you dev account, your care account, and your prod account. In my case, I have just used one account to keep this example simple. But if you would set up it right, then this would be 4 accounts. And then you would need also exactly the roles to make a cross-account access possible to the pipeline from your toolchain account, right? So that's why we have these bootstrap stacks. And then we have all these stacks, as mentioned, to be deployed. And once you kind of create the project for the first time, there's one thing you have to do. So you have really to, let me see, you would really have to do a CDK deploy pipeline stack. So, or prod pipeline, I think it's named CDK pipeline, CDK pipeline. So you would have to do a CDK pipeline, which will then deploy your pipeline. Let's have a look how this looks like in our account. So once we deploy our pipeline, CDK deploy, we would have this one. There's one more file before the actual pipeline. This is a CDK toolkit. This is actually the very first thing you should do is a CDK init, right? And then a CDK bootstrap, which will deploy this toolkit. And then the CDK deploy pipeline stack will deploy our pipeline. So we can have a look here on this pipeline. You find this in the developer tools pipelines. And here is this example. We have here a couple of actions. As you can see, the first one is the source action, which pointing to my GitHub repository. It can be a GitHub, it can be a Bitbucket, it can be a code commit repository in the AWS. So this is exactly pointing to my project, and therefore it will find all the CDK files which is going to be deployed. Then I have a build file. This is actually doing the synthesizing commands, which you normally would do if you would have no pipeline. You do a CDK synth, right? And this is checking your syntax of all your CDK classes, and this is also then really generating the CloudFormation files, which are here in the CDK out folder. For example, if we have a look on the roles here, you can see here is a JSON. It's the format is always JSON of the generated files, and you will see exactly these files are then going to be deployed by the pipeline. And this build command is actually doing the CDK sync command, which I'm doing right now, and is going to create all these kind of output files for the deployment. And if there would be any syntax error, the synth and the build step here would already fail. There's an update pipeline step, which is important because sometimes you may have to really change your pipeline itself. We can have actually a look, how does the pipeline really look like? So if we see our project here, I have only showed so far the main files. You can see here in our infrastructure all the CDK files, and here under CI/CD, I have a pipeline. And this one is showing already the features we can use in a object-oriented languages. As we can see, we have this project pipeline stack, and it has a superclass pipeline stack. Therefore, I have here a generic folder which kind of demonstrates the usage of these features. In the generic folders, I have again an infrastructure, and here are supposed to be the files which are generic and reusable, or which are superclasses. So for example, here again is CI/CD, and here's the superclass, and here's actually all the code to create the pipeline. And in my project pipeline, I'm just calling the constructor. I'm just having a simple example of how to override a method of the superclass if my project, for example, needs some different unit tests or some different commands to be. But actually any method here in the superclass for the pipeline can be overwritten by a child class, by a project pipeline stack. So as we can see here, we are creating our code pipeline. We are needing some kind of source input, which is my Git repo, but could be any repo. And then we are having here the synth step we have seen, and we have the code pipeline in itself. And maybe we want to do some changes here. Sometimes we want to change the roles, or we want to change the build environment. We want to set privileged false. This would need to update the pipeline, right? And therefore, we have the update pipeline step, which is able then to change its own resources, right? So you cannot create it the first time. That's not able for the pipeline, but the pipeline can update itself. And then we have here these stage files I have talking about, and in this way, I have, as you can see, this is of kind of class stage. I have a toolchain deploy, which you can see here, and you can add your resources which you might need deploy in the proper toolchain account, and then you would have to, at least one other stage, which is going to represent the real stages like the dev, QA, and prod, right? And here I have these, I call it app deploy, the stage for our real stages, and I'm adding here some example some simple examples, because this is just a demo. I have a S3 bucket, some job definitions for a batch, and I have a Lambda file. This would be really maybe grow real bigger in a real environment, because actually on the stage file you would add kind of all these resources which are going to be deployed, for example, in the dev account or prod or whatever. So there would be really everything layered, maybe by first the VPC, then the storage like S3 and databases, then the applications, and final the monitoring. So in a bigger project you might have here maybe 20 stacks. And each of these stacks, of course, is kind of a composition with a couple of resources. But as you can see here, we have, for example, our action to deploy the toolchain. And we can see here, we are deploying this ECR repo we have just seen. And there's always a prepare and a deploy. We can also see we have here tests before executing the prepare and deploy, Lambda tests and unit tests. This is again defined in the pipeline, right? So you can not only add your stages here in the pipeline, but you can also, once you have added the toolchain stage, you can also, for example, add tests to these stages. For example, here is infrastructure unit test, and here's Lambda tests. They be added to this toolchain stain. That's why you find here on the toolchain chains these two test units. And then we have the dev stage. And here again, I have different tests. I have acceptance tests and integration tests. And you can see this here is the deployment, the dev stage added. You can see it here. And again, here we have the chance to add integrations test, acceptance tests, or whatever we might think which would be a good use case for our deployment here. In the project, for example, you can see these tests here. These are unit tests for the infrastructure classes, and there's also a test folder for these two. We can see here the acceptance and the integration test. Right, so the pipeline runs from checking out the project, from synthesizing, from maybe updating itself. Normally this is going to be skipped. Then it will deploy all the files which are defined in the toolchain stage on its own account, and then it will deploy, for example, the files which are defined in the dev stage to the dev account. In my example, as you have seen in the CDK JSON, I have only defined for this example and for this meetup one account for everything. So what we can see here, this was our pipeline which was created first. It then deployed the toolchain ECR repo stack, which is still correct here in this account. But as you can see here, it then deployed the dev stacks also in the same account, because I haven't made their differentiation, so it's deploying these. But actually, think of these 4 stacks are part of the dev stage, so these should actually only be visible in a different account where we do a switch role, and then we could see, okay, these are my resources I want to deploy to my stages. Right, and then what we can see here, we have added a dev. And then we have added a manual approval step. So once the pipeline succeeded here, actually it didn't succeed, so we cannot approve here really successful, because I had somehow integrated an error here in the update for the integration test. But if this integration test would have been succeeded also, we can send here review and say, yes, I want to approve. And then it will deploy on the QA, it's the same stacks again, so to my QA account, right? So we first need to deploy successfully on dev, then we approve, every test have been succeeded, and then we go to QA. And we could do the same thing after QA with a manual approval with prod, and then deploy to prod. Or what we could actually do, I have just deployed here in my pipelines one pipeline, the CDK pipeline, as you can see. But if you have seen on the CDK list command, we had here in our main app Python, we had here actually 2 pipelines, right? I had created, it's still the same file for CDK, but I have just passed a different second parameter. I have created a pipeline for QA and dev. This is the one we have seen, but we have also a prod pipeline, which I doesn't have here deployed. And if you deploy this pipeline, then you would see here a prod pipeline, and that's a good practice to really separate the prod pipeline in a different one if you really want to control better kind of the access here. And yeah, so that's basically, I think that's a lot of stuff in this time. You need really already maybe some CDK basics or experience to start deploying with a code pipeline with CDK. But if you have this experience or you have the interest, please check out this project and try to deploy with the pipeline. And yeah, have a lot of fun deploying these resources. So far for this, as mentioned, you find the project here. You find some also here a blog about the CDK pipeline and some more pipeline stuff, how to pass variables, how to use Git submodules, how to create pip modules with CDK. So a lot of stuff in this blog. And I think for now, this is kind of the stuff I wanted to show here. So any questions?
Thanks a lot, Wolfgang. Yeah, so so now it's the time for questions. So I have one question.
Mm-hmm.
You mentioned at the beginning about Terraform, right? So I mean,
Right.
I myself work with Terraform before, and so what do you think is the biggest advantage of CDK comparing to Terraform?
As I already mentioned, for me, I like more the programmatic approach from the CDK. I really like to code in Python, or if somebody likes to code in Go or Java or whatever. As I said, you have also by now the Terraform CDK, which kind of clones the functionality of the CDK. So you can code by now also Python and Go, which will then generate Terraform files, as the CDK does when it generates CloudFormation files. So then you can reach with Terraform CDK kind of this functionality. If you use just Terraform or TerraGrant, you are limited to the ACL features, and you have basically text file. You have still some kind of features like for each, but you have not a full object-oriented language support. So you're limited, like CloudFormation. And for me, from my experience, what I also mentioned there on these slides here, I had experience with bigger teams with Terraform, with the Terraform versions. So somebody say, you know, it's not like this anymore, but in the time I worked with Terraform, there was like any week a new release. And so if you have 8 or 10 team members, comes in a Terraform version, one of your team members makes an update, then applies the change, and it doesn't work for the other 9. And then everybody again has to update. So you need to take care that all of your 10 team members have the same Terraform version. And the second disadvantage I've seen there is Terraform, at least at this time used to have sometimes problems with the state. So the state handling was sometimes kind of a pain in the ass. So if you run in a problem there, you're busy for one day to get it fixed. So and that's what I have seen as a disadvantage of Terraform. But it's also my kind of personal idea. So I know a lot of people like Terraform. If I have a free choice, I would always prefer the CDK before Terraform.
Yeah, okay, thank you. Did you ever experience, because CDK is, from my understanding, is only for AWS, right? Did you ever experience the fact or the situation that you have to switch from one cloud, so from a AWS to a different cloud provider? Did you already have it, and how did you deal with this situation?
As mentioned, I have never faced the situation so far. That's why I also said for me, this cloud agnostic, advantage, I wouldn't rate it too high, because I don't know if you had already project in your company when you migrated environments from Azure to AWS or vice versa. I have never done so far in my experience a project where somebody really moved all its environment from AWS to Azure. I have not faced it so far. It might happen, but yeah, it's for sure not a daily business. So, and I was so far not confronted with this experience. So I think I would like to kind of use the more AWS native features. So I think if I go to AWS and I have a commit, you have also getting better prices and cost saving. If you have a commitment, for example, for 3 years, you get reserved instances, compute saving plans. So you should make up kind of your choice for a time. And if you go to cloud and think maybe I'm gonna go to Azure in 6 months. It's not so easy to switch if you're using step functions, lambdas, or also all kind of stuff. You will not be able to switch these features to a different cloud provider. You can switch your EC2 instance, of course, or your databases, but there are so many features on AWS, like CloudWatch events, Event Bridge, step functions. You won't be able to migrate this to Azure or Google. Even if you're using Terraform, and you cannot just switch the provider and then deploy your resources then on Azure like they used to be on AWS.
Maybe a thought from my side, without claiming any big expertise in the AIC environment. I have worked for big clients that actually had a multi-cloud or a hybrid cloud environment, and I could imagine it could make a difference there, while fully recognizing what you're saying, Wolfgang, that the clouds themselves can be so different that is difficult to apply these sort of standardized environments across multiple clouds. Just my 2 cents.
Yeah, I think it makes sense if you really already have a multi-cloud environment, and then I think Terraform is a good choice. So if you say already I'm having in this module my AWS resources, I'm having here my Azure resources, but you won't mix up these, right? So you won't probably you will not deploy your AWS lambdas later on to Azure functions. So in this case, you have just one infrastructure as code tool, Terraform, which is able to deploy to both clouds, and then I think it's a good choice.
And then still you have to pay attention like hell.
Yeah.
Yeah, so I also experienced in the past that usually big clients like Volkswagen, BMW, and so on, they have multiple clouds. So this is something which happens a lot from my experience, that the clients say, okay, they don't switch completely, right? So it could be the case that they say, hey, now we use Azure, but in the later stage of the project, because usually because of policy, because of politics, because sometimes the product owner, he say, hey, we do get data via Azure, so we have to go for AWS because they have because the guy from AWS in the company is react faster. So the choice of switching the cloud provider is usually very, very, very funny. So you might have very funny. Yeah, it's painful. Yeah, this is something which can happen. So that's why, from my own taste, I really want to stay open source. I want to stay cloud independent, but maybe it's just me, right? Maybe
I know it for the, I only know it for the very big corporations. That's first, because everybody else tries to simply optimize their cost. And the second thing I know it for actually is for security reasons. And I just witnessed a conversation a couple of weeks ago where somebody was saying, well, you know, you have all of these different zones, as they're called, in the various cloud providers, and we have enough redundancy. I mean, why would we have several cloud providers as well? And I think 2 days after that, the entire Microsoft cloud went down. You know, we couldn't use Teams for a day, and and of course the discussion stopped after that. You know, that was it. Yeah.
Yeah, I think really enterprises using multi-cloud, but yeah, I mean, I'm doing also a lot of projects for tech companies and stuff, and normally that's also the projects I like to do. The tech companies normally using heavily Linux servers and all this stuff, and using more AWS, where I think more the industry companies, the companies who have maybe production have a production of whatever kind of machines or stuff, and already have some Windows workloads using all the Outlook and Office programs. They might then migrate to Azure. But so from my choice, I will always prefer working on AWS than on Azure. That's my choice.
Yeah, I can also second here to Wolfgang from my experience before at Bosch. So from the cost perspective, we always prefer AWS because they also have very nice and advanced features. But then the choice of having multiple clouds are also sometimes made on purpose to maintain, or let's say to balance between the different monopoly of the different cloud providers. So, for example, in our team here in autonomous driving at Bosch, we purposefully choose 3 clouds at the same time for different projects, not because that's save any cost. Actually, will cost a lot of money for maintenance, but because then we can go to any cloud provider and say, we are not the only provider that we have, and the data are also spread over different providers, and we have a much better position when we negotiate about different feature and things. So that's sometimes also the strategy that's decide why we go for different clouds. Also, we know that it doesn't save any cost. So that's also one perspective.
Yeah. I think it's good there. It's not a monopoly, right? So you have different cloud providers, but I don't think if you as a company has to make this choice to use 2 or 3, I don't know if you really get better prices. If you talk to AWS, hey, I'm also using Azure, so if you don't give me these discounts, I will switch. I mean, these prices are also kind of standardized, right? So it's good. There is Azure, there's Google. So AWS has to kind of make competitive prices. I don't know if you really can discount them with kind of trying to tell
I don't
them.
think we care about the price. I mean, the price is one factor, but the influence on the strategy and the ask for the velocity of support, and also some other security perspective is what the big factor here.
Yeah, you can talk, you can negotiate just about anything with them, but you have to be very large. You know, I mean, we're talking about Corporate 500 in the US, then you can do that, but otherwise it's difficult. They have their standard prices, their standard conditions. They obviously don't want to mix these up too much. Yeah, if you have your own key account and you want one of those very large account models, then you can negotiate almost anything, but other than that, it's very difficult. Gentlemen, I have to leave because of family commitments. I'd like to thank both speakers. Been highly interesting, both talks. Thank you very much. but I need to leave now, so I may see you in another occasion. Thank you very much, and goodbye for now.
Bye.
Okay.
Thanks.
Bye bye.
Thanks,
Bye.
Edward.
Thanks.
Yeah. Yeah. So I also make the experience that cost doesn't matter so much in bigger corporations. So I mean, when I was in a project for a big automotive company, so the first thing I did was I was trying to optimize the cost, right? And the product owner from this big automotive company just taught me that that cost doesn't matter to them, especially in the first of the prototype phase, because usually the big corporations, they have like reserve resources, and they pay a huge amount of money to reserve these resources. So usually, well, it depends. I mean, in the future, it certainly is going to play a huge part. It's going to play a huge role to save costs, but I make the experience from my point of view that first, the company, the big corporation, they don't concern a lot about saving costs. They want to make things work. They want to make things functional. This is the first point. And the second point is they don't want to depend on just one cloud provider. They want to be multi-cloud, so that they don't depend too much on one cloud.
I think they want to keep the option, so they want to don't want to really stick. We are using AWS. They want to use both, and or more. I can understand it, but you know, from a infrastructure as code view, for me as a DevOps, if I don't have these kind of classes, I'm just seeing how can I deploy my infrastructure as code or my resources the best way to AWS, leaving these political decisions out of view, then I would prefer perfectly, for example, if I do an AWS project, I would do CDK. I wouldn't use just Terraform because it gives me kind of a cloud agnostic option. I wouldn't do it.
What I like the most annoying foot guns about CDK.
The most annoying.
Yeah, like where you like that maybe beginners like easily fall into, except maybe recursive lambda functions.
Well, I think CDK is if you get started, you need a little bit more time to get into it, to kind of understand how are these constructs built. Level 2, where should you use like maybe a level 3. The whole setup, the project setup is a little bit more complicated. Sometimes you have, for example, I'm using Python. In other languages, you might have other trouble, but sometimes with Python and with doing installing the libraries, it can be a track. So if you're updating libraries in Python, and sometimes you might get in conflicts, so these kind of stuff. But CDK itself, it's working quite well for me.
Okay.
Okay. Any more questions?
No more questions, Wolfgang, but thanks a lot for the conversation, for the very interesting talk. And all right, then Alex, also thank you. Thanks a lot for your talk as well.
No problem.
And so I would say let's close the session. I will send you guys the video recording. And again, thanks a lot.
Thank you also.
Have a nice evening.
See you around all
See you,
sometime.
bye.
Have a nice evening.
Thank you. Thanks a
Bye.
lot.